Welcome to lecture 42 on risk management and insurance. This will be the last lecture of the course. It will be quite a short lecture in which we just give an example for stochastic dominance. Let's first repeat again those graphs here from slide 365. Remember, we have the cumulative distribution function. That's a probability density function. When you integrate the probability density function, you get the cumulative distribution function. And when you differentiate the CDF, you are back at the PDF. So the two graphs actually have the same information. Now, in introductory classes, statistics classes, maybe you are more used to the PDFs. You will see those graphs more often. So when you draw a normal distribution, typically they draw in those textbooks, they draw the probability density functions, the PDF. But in practical work, it's sometimes more convenient to use the CDF, the cumulative distribution function. And that's what we have done last time. We used the CDF to explain stochastic dominance. But I could have made the same story using the PDF, because that's just more common than actually here to use the CDF. So that's just something that we should keep in mind. So today, again, we'll use the CDF, but in the background, naturally, there is a PDF, and we could do exactly the same example I do today. I could actually try to explain with a PDF, but it would be somewhat more difficult to do. Now let's share a new slide. Okay, so let's go to a case study on crop rotation. Now, crop rotation is when a farm is planting different plants or different crops from year to year. You see, a farm should not actually plant every year the same crop, because this will actually damage the soil, and then yields will start to decline. So you do crop rotation. Maybe in 1 year the farm is planting wheat, then the next year they are planting corn, and then the year after that they are planting lupines, and so maybe after a few years they are back to wheat, and they just rotate the plants. They rotate the crops from year to year, and that's better for the soil. So it really does not exhaust the soil, and so the yield stays up. It's also actually better against illnesses, okay, against fungi and whatever illnesses the crops can have can be damaged. It happens less. The crops are more robust, okay, if you actually plant different things from year to year. So a farmer, let's assume the farmer now has to evaluate different crop rotation schemes. So it can be done in different ways. Maybe he goes wheat, lupine. Okay, that's one way of doing it. Maybe the other way of doing it is actually wheat, and corn, and so on. So you can actually think about different schemes of crop rotation, different ways of doing it. And let's assume the farmer has now the information. What is the output, the likely output of each scheme? Naturally, it's just a likely output. Okay, it will be given by a probability distribution. So the yield will be given by a probability distribution. And the different ways of crop rotation schemes will give us different probability distributions for the output. And then the farmer has to somehow to decide, okay, which output should he or she take. Now, so here we have the crop rotation schemes, F, G, H, I, J, they call them. And okay, go up to k. So we have here actually 6 ways of doing it. We have evaluated 6 ways of 6 different crop rotation schemes. And here in the columns, we have the outputs. We have the probability distributions. Now, what we give here are the so-called fractiles. That's a value of a distribution for which some fraction of the sample lies below. So maybe here the 40% fractile. So for scheme F, the first scheme, 40%, okay, the chance is 40% that we have less than 272 here as output. However they measure it, okay, maybe that's actually tons per hectares for wheat or whatever. So when you look at here, okay, so we have 40%, it will be less than 272 the output. That's for F, the 40%. Yeah, that's about right here. Okay, so 40%, that's about here. Okay, so that's maybe 272. Yeah, here we have 300, here we have 400. So that's about right. With a 40% chance, the output will be less than 272. Now the top here, that's a best output here. That's somehow 500 something. So with 100% chance, we will have an output of less or equal 500 something. Let's see whether that's true. Yeah, okay, 540 here. So with 100% chance, the output will be 540 or less. So basically what the numbers here give us, they just give the cumulative distribution functions, the empirical cumulative distribution functions. And we get it for those 6 types, for 6 ways of planting the crops. So each crop gives us actually another cumulative distribution function for the output. But then remember, we could also actually do the probability density functions. Okay, so the probability density functions, you're more used to it in introductory classes. Okay, so one for the normal distribution just gives a nice hill, symmetric hill, and so on. But we work now here with the CDFs. So the question is, okay, what should the farmer do? Which is the best crop rotation scheme? Now, how does the farmer get those data? That's naturally not easy. Maybe, okay, that he has observed, she has in the past. Okay, maybe in the past different crop rotation schemes have been done, and then okay, they just use those data. How you get the data is naturally a difficult question, but I will not discuss it here. You have to go back to the Hardrecker book, okay, and then they probably refer to some sources. So you can use stochastic dominance to decide between those risky prospects. Each crop rotation scheme is a risky prospect. Each one has a different probability distribution of outputs. And those probability distributions we show actually now by the CDFs, the cumulative distribution functions. So we can use it in 2 ways. We can use this actually to predict how the farmers behave. Okay, that's a positive theory, but naturally we can also use it actually just for the farmer. And the farmer can use this, okay, how he should behave. Okay, what is best for the farmer to do. Now, you compare the different schemes pairwise. And if you have more than 2 prospects, and once it has been established that one prospect is better than the other, then you no longer have to look at the second one. So it's really not necessary to look at all the possible pairs of prospects. You just start, you compare 2, then one is actually better than the other, maybe, and then if that's the case, okay, so once that's excluded, you never have to consider it again. Okay, so you don't have to do all the pairs you just move on to the next one, to the next comparison. Now here I have I plot here, I do it just for 4 of those 6, F, G, J, and H. So that's the data plotted for F, for G. So again, for example, so 50% here, okay, with 50% chance we are below 299. Okay, so that's let's do. So 50% here, yeah, okay, that's about right. Here we have about 300. So with 50% chance, we are below 299. Okay, so for scheme F. Now for scheme G, that actually with 50% chance, here we are below 326. That's a 50% fractile. So with 50% chance, it's a bit higher here. It's actually not 299, it's now 326. So with 50% chance, we are below this somewhat higher value here. So I just simply plot the CDFs for the different schemes. I only do it for 4 ones. I don't do it actually for the last 2. So I do it here for 4 schemes. Okay, I don't plot all 6. And then you can use what we discussed in last lecture. G first order dominates F, and H first order dominates G. You see, G is better than F. For G, whatever the probability here, we have here a higher output. We are faster to the right. Okay, so G is always better than F. So forget about F. Okay, we just can exclude it. And the same is actually happens to the G. You see the H is actually always better than the G. So let's now forget about the G. But we have, so H is actually first order dominating G and also F. G first order dominates F and H first order dominates G. And actually H first order dominates both of them. But then we have here the crossing CDFs. So here we cannot do first order dominance. Here we have to do second order dominance. And remember, second order dominance, here actually we must make stronger assumptions on the utility functions. We do not simply assume that people prefer more to less. That's what you do. Okay, you see G is always better than F. Okay, you always have more here. Okay, it's always more here on this axis, more output. So obviously G is better than F. Okay, so in the end, it's actually common sense here. You see, we have the scheme G just gives us always a higher output. Okay, so it's better if we prefer more to less. Same thing for the H. Always we have more than the G and the F. So we have here first order dominance. So we rule out F and G, forget about them. But then we have the problem here with H and J. Say cross here. J is better here, you see. And it's actually better over quite a long distance. And so it does not matter that actually H starts to become better here when you calculate the expected utility. Okay, it's still actually here, the expected utility is so much better for such a long distance. Okay, so that actually here it turns around, H becomes better, but on net, J is still better. And that happens if actually this area in between here, if this area in between here is bigger than the area in between the 2 curves here. So actually J will second order dominate H. And so the farmer should go actually for scheme H. Okay, if the farmer prefers more to less and is risk averse, then the farmer actually does a planting crop rotation scheme J. That's the best thing the farmer can do. That actually maximizes expected utility, expected output. So again, you have here for down in this range, J is obviously better than H. But then up here, actually H starts to become better than J, but only over a relatively short range. And so actually this error is less than that error here. And so in the end, actually J is overall, on net, is overall better. It gives us the higher expected utility. So that's, we have those three definitions. Now if you have here second order stochastic dominance, it's also about expected utility. You see, we want to go for the one with the higher expected utility. Okay, here it's inequality. And we can compare here than just, okay, here we had done it for the first time on this graph. Okay, good. Now I have, so H can be excluded because J second order dominates H. So H can be excluded because J second order dominates. We should go for the J. And then actually based on first order and second order stochastic dominance, we cannot distinguish between J, I, and K. I don't include those here in the graph. So the efficient set, then you can actually, the farmer actually should take one of those three, I, J, and K, but I have not shown it in the graph. Now to distinguish between I, J, and K, then again you must make even stronger assumptions on the farmer's utility function. For example, you may assume that the coefficient of risk aversion lies within a certain range. So you still do not completely use a utility function with the parameters. You just say the parameters of the utility function are in a certain range. But now when you make stronger and stronger assumptions, and in the end you have the utility function, maybe those assumptions are actually wrong. Okay, so that's actually a drawback if you come up with stronger and stronger assumptions. So it's maybe in practice, that's all what can be done. Okay, with this example, okay, the farmer then uses I, J, or K. I, J, or K. So he will, the farmer will play around with those. Naturally, if you know the farmer's exact utility function, then you could say, okay, what is best for the farmers? But maybe you just really don't know that utility function. It's not so easy to estimate those utility functions. So that's practical work they do, okay, in agriculture economics. Agriculture economics has naturally to do quite a lot with risk, because okay, you have the risks that it rains, it's risky. You don't know in advance what your crop will be. You only, maybe at best, you know the probability distribution. Here I assumed that you know the probability distribution, but even to know that probability distribution is not so easy. Now the probability distribution I gave you here is a CDF with those fractals. Just give you the CDF. As I said, we could have done this story also with a PDF, with a probability density function, but it's now in this literature, so use the CDF. Okay, so that finishes this lecture, and it actually also finishes the entire course. So thank you very much.